Hi, welcome back to my algebra class. In the last lesson, we took up multiplication of algebraic expressions. And in multiplying algebraic expressions, we apply the properties of exponents and the distributive property of multiplication over addition. There are certain products that frequently occur in many applications of mathematics, as well as in advanced topics in mathematics. And to simplify the process of obtaining the product of these special products, there are certain rules to simplify the process of multiplication, and we call these rules the special product rules. For today, we will take up three special product rules. The first one is the product of a sum and difference. In this special product rule, we are multiplying two binomials. The first binomial is a sum of two terms, and the second binomial is a difference of two terms. That's why it's called the product of a sum and difference. The second special product rule that we will take up is the square of a sum. In this special product rule, we are multiplying the sum, a binomial by itself, and the operation involved between the two terms of the binomial is addition. That's why it's called the square of a sum. And the third and last special product rule that we will take up today is the square of a difference. In this special product rule, we are multiplying a binomial by itself, and the operation involved between the two terms of the binomial is subtraction. We start with the first special product rule. It's called the product of a sum and difference. Rule number one, we are given the product of a sum of A and B, and the difference of A and B. We are multiplying. We want to get the product of a sum and difference. And according to this special product rule, the product of this sum and difference, the sum of A plus B, and the difference of A and B is equal to the square of A, the first term, minus the square of the second term, B. You notice that in these two binomials, the first term is the same A, the second term is the same. They only differ in the operation between the two terms A and B. In the first, we have a sum. In the second binomial, we have a difference. We can easily verify that the product of this sum and difference is equal to the square of A minus the square of B by applying long multiplication, by multiplying this binomial by long multiplication, and we do that now. We want to prove that the product of A plus B and A minus B is equal to the difference of the square of A and the square of B. We distribute A from the left side to each term of A minus B. A multiplied by A by property of exponent, common base is A. And we add the exponent of A. We have the exponent of A here is 1, the exponent of A here is 1, and 1 plus 1 is 2. Now we multiply A by negative B, we get negative AB, the product AB. Now we distribute B from the left to each term of A minus B. We multiply B by A, and we multiply B by minus B. B multiplied by A is BA, but by commutative property of multiplication, the product BA is the same as AB. So positive B, multiplied by A is BA, or we write plus AB. And B, positive B multiplied by negative B, positive multiplied by negative is negative. And the common base is B. Again, by property of exponent, we add the exponents of B here and the exponent of B here. Exponent of B here is 1, plus the exponent of B here is 1, we get 2. After multiplying, we simplify by combining like terms. Only the middle terms are like terms. And they are the same quantity with opposite signs. So their sum will add up to 0. That is AB minus AB is 0. Or minus AB plus AB is 0. And this simplifies to A squared minus B squared. Thus, we have shown that the product of a sum and difference, the product of A plus B and A minus B, is truly equal to the difference of the square of A and the square of B. We now take an example to apply this rule. Example 1. We multiply 3m minus 5n by 3m plus 5n. In this given, we have a sum and difference. But in this given, the first factor is the difference of 3m and 5n. And we can still apply this special product rule number 1 because multiplication is commutative. In this product, A minus B can come first or ahead of the factor A plus B. Also in this sum, 3m plus 5n may come before 3m minus 5n. But in this given, if you compare this given to the special product rule number 1, you see that A is 3m. The first term of these two products is the same, 3m, and the first term is denoted by A. You can also see that the second term in these factors is the same. The second term is 5n. And the common second term is denoted by B. So our B is 5n without the sign. Both A and B are positive. And the product of a sum or difference, or the product of a difference and sum, is equal to square of A by special product rule number 1. The product of a sum and difference is the square of A minus the square of B. And we replace A with its value. A is 3m. The square of 3m minus the square of B. B is 5n. And we take the square of each term by applying properties of exponents. The square of a product 3m by property of exponent equals the square of 3 multiplied by the square of m. The square of 3 is 9 multiplied by the square of m. And we get 9m squared minus the square of 5n by property of exponent equals the square of 5 multiplied by the square of n. And And the square of 5 is 25. Multiply by the square of n. We get 25n squared. The square of 5n equals the square of 5, 25. Multiply by the square of n squared. Thus, the product of 3m minus 5n and 3m plus 5n equals 9m squared minus 25n squared. We take another example for applying the first special product rule. The special product rule for the product of a sum and difference. We are given 3xy multiplied by 7x plus 2y squared multiplied by 2y squared minus 7x. By inspection of these two binomials, 7x plus 2y squared and 2y squared minus 7x, you can see that both binomials have 7x. Both binomials have 2y squared, 2y squared. But these two terms are not in the same order. So to be able to apply the special product rule number 1, we either rewrite this one or we rewrite this one so that the first terms are the same in both binomials and the second terms are the same in both binomials. I will rewrite this binomial 2y squared minus 7x by factoring negative 1 from 2y squared and 7x. I will factor out negative 1 and multiply by 3xy. We get negative 3xy. Multiply by 7x plus 2y squared. Multiply by, now we factor out negative. Negative 7x divided by negative is positive 7x. Or negative divided by negative is positive 7x. Here, divide 2y squared by negative, or divide positive by negative is negative 2y squared. Now you can see that the two binomials have the same first term 7x and the same second term 2y squared. And in the first binomial we have a sum, in the second binomial we have a difference. Now we can apply the special product rule number 1 to find the product of the sum and difference. By special product rule number 1, the common first term 7x is our A. And the second common term 2y squared is our B. B equals 2y squared. We have negative 3xy multiply by special product rule number 1, the product of this sum and difference using A and B is given by the square of A minus the square of B. We substitute A, we replace A with 7x, we replace B with 2y squared. Negative 3xy multiplied by A is 7x raised to 2 minus B is 2y squared to the power 2. And we simplify, we get negative 3xy multiplied by Again, apply the property of exponent. The square of 7x equals the square of 7 multiplied by the square of x. The square of 7 is 49. You write 49 multiplied by the square of x, x squared, minus, again by property of exponent, the square of 2y squared is equal to the square of 2 multiplied by the square of y squared. The square of 2 is 4 multiplied by the square of y squared. And to get the square of y squared, we apply another property of exponent. You have an exponential notation, raised to another exponent 2. And by property of exponent, we simply multiply the exponents 2 multiplied by 2. And we get y raised to 4. Finally, we multiply each term of the binomial by negative 3xy. And negative 3 multiplied by 49 is negative 49 multiplied by 3. 9 by 3 is 27. Carry 2. 3 by 4 is 12 plus 2 is 14. Hence, negative 3 by positive 49 is negative 147. Negative 147. X multiplied by x squared is common base is x. Copy the common base and we add the exponents of x. 1 here plus 2 here is 3. And multiply by y. Negative multiplied by negative is positive. And 3 by 4 is 12. And multiply by x. And multiply the factors y. And y raised to 4. Common base is y. And we add the exponents of y. 1 here plus 4 here is 5. And that's the product of the given 3xy multiplied by 7x plus 2y squared multiplied by 2y squared minus 7x. Again, when you see two binomials in the given product and they have the same first term and the same second term, only they differ in the operations between the two terms in the two binomials, you know that you will apply the first special product rule. If both terms appear in both binomials but in different order, you have to rewrite first, as we did in this example. Rewrite the order of the terms of one of the two binomials, so that the two binomials will have the same first term and the same second term, and they will only differ in the operations between the two terms in the two binomials. We now take the second special product rule, known as the square of a sum. Rule number 2, we are given the square of a sum of two terms, or the square of a binomial, in which the operation between the two terms is addition. And according to this special product rule number 2, the square of a sum is equal to the square of a, or the square of the first term a, plus twice the product of the two terms a and b. Or the second term is positive 2 times the product of the two terms a and b. The first term is a, the second term is b. And the last term is the square of the second term. of the given. The second term is b. Again, it's easy to verify this, that the square of the sum a plus b is equal to a squared plus 2ab plus b squared by applying the property of exponent to the left side and using long multiplication. And we do that now. We verify that the square of a plus b is really equal to a squared plus 2ab plus b squared. By beginning from the left hand side, applying the property of exponent, the square of a plus b means that we multiply a plus b by itself 2 times. In this exponential notation, the base is a plus b and the exponent is 2. And a plus b square means that you multiply the base a plus b by itself 2 times. 2 times because the exponent is 2. We multiply a plus b by a plus b. Hence, at the right hand side, we have written a plus b 2 times. And we distribute each term of the first factor to each term of the second binomial or factor. We start with a, multiply a by each term of the second factor a plus b by applying properties of exponents. We have a multiplied by a, common base is a. And by property of exponent, we add the exponent 1 here. And the exponent of a here is 1. And we get the sum 1 plus 1 is 2. We multiply a by b and we get the product ab. Now we distribute the second term of the first binomial to each term of the second binomial. We start with b multiplied by a is ba. But the product BA is the same as the product AB, since multiplication is commutative. So instead of writing BA, we write plus AB. And finally, we multiply b by property of exponent, copy the common base b. And we add the exponents of b. Here we have 1. And here the exponent of b is 1. And 1 here plus 1 here is 2. So the product of b by b is b to the power 2. Or we write plus b squared. And after removing the grouping symbols, we simplify by combining like terms or similar terms. And you can see that the middle terms are the like terms or similar terms. We have the second term is AB, numerical coefficient is 1. And the third term is AB, numerical coefficient is 1. So we combine the two middle terms, the second and the third terms. The first term is the same, a squared. And to combine like terms, we add the numerical coefficients. 1 here plus 1 here is 2. And we copy the common literal coefficient AB and plus the last term b squared. Thus we have shown that the square of a sum is truly equal to the square of the first term plus twice the product of the two terms plus the square of the second term. This shaded rectangle here indicates the end of proof. We now take an example for applying the second special product rule. Suppose we want to get the square of 7p plus q square. We want to get the square of the sum 7p plus q. Instead of multiplying 7p by q by itself 2 times, we apply the second special product rule. The first term a now is 7p. A is 7p. And the second term b is q. And according to the second special product rule, the square of 7p plus q using a and b is equal to the square of a plus twice the product of ab plus the square of the second term, b. And we substitute a and b. A is 7p, and we square it, plus 2 multiplied by a is 7p, a is 7p, multiplied by b is q, plus the square of b, and b is q, square it, q is squared. And simplify is termed by property, by applying the property of exponents. The square of 7p by property of exponent equals the square of 749 multiplied by the square of p squared plus 2 by 7 is 14 multiplied by p multiplied by q. And the last term is the square of q. That's the square of the given square of 7p plus q, obtained by applying the second special product rule, the square of a sum. We take another example for applying the second special product rule for the square of a binomial. Consider the following. We have the square of x plus 2y plus 5c. In this given, we have the square of a trinomial, but we do not have a special product rule for the square of a trinomial. So what we will do is we will express this given as the square of a binomial, or the square of a sum of two terms. So we can apply the special product rule number 2 for the square of a binomial. To express this as a square of a binomial, either you group the first two terms as one term, or you group the last two terms as one term, and then apply the second special product rule for the square of a sum, or the square of a binomial, in which the operation between the two terms is addition. I will group the first two terms as one term, and to rewrite this as the square of x plus y, group them as one term, x plus 2y plus 5c squared. Now we have rewritten the given, the square of trinomial, as the square of a binomial. This is the first term, and this is the second term. The first term is another binomial, but we have a square of a sum of two terms, one binomial and one monomial. And to get the square of this sum of two terms, we now apply the special product rule number 2 for the square of a sum. And the square of a sum says that the square of a sum is equal to the square of the first term. The first term is a binomial, x plus 2y squared, plus the second term is twice or 2 times the product of the two terms, The first term is x plus 2y. Multiply by the second term 5c. And the last term is the square of the second term. The square of 5c. The square of 5c. And we simplify each term by applying properties of exponents or another special product rule. As in the first term, we have a square of a sum. So to simplify the first term, we apply again the special product rule number 2 for the square of a sum. And this special product rule number 2 says that the square of a sum is equal to the square of the first term. The first term is x, and square it, you get x squared. And the second term is twice or 2 times the product of these two terms. Twice multiplied by x multiplied by 2y. And the last term is the square of the second term, 2y, the square of 2y, plus the square of 2y, plus 2 multiplied by 5 is 10. Multiplied by z is 10z. So we multiply x and 2y by 10z. Or we multiply x by 2 and by 5z. And we get 10xz. 2 by 5 is 10. Multiplied by x, multiplied by z, 10xz. Plus, we multiply 2y now by 2 and 5z. We have 2 by 2y is 4y. 4y multiplied by 5z is 20yz. 20yz. Plus, the last term is the square of 5z. And the square of 5 is 25 multiplied by the square of c. We get 25c squared. 25c squared. And we simplify further the second term and the third term. X squared. The first term is x squared plus 2 by 2 is 4. Multiplied by x multiplied by y. Plus the square of 2y equals the square of 2 multiplied by the square of y. We get 4y squared. Plus 10xc. The rest of the remaining terms are as is, plus 20yz. Plus 25 c squared. This is the expansion or the square of the trinomial x plus 2y plus 5c. You can also rewrite this as the square of a binomial where the first term is x and the second term is the sum 2y plus 5c. In this solution, we group the first two terms as one term. So we can write the square of this trinomial as the square of this binomial, where the first term is another binomial. Or you can rewrite this given, the square of trinomial, as the square of this binomial, where the second term now is the sum of 2y plus 5c, which is another binomial. And you may want to try expand this, apply the second special product rule to this, and apply again the special product rule, the second special product rule to the binomial 2y plus 5c, and you should get the same terms and the same number of terms. We now take the third special product rule for the square of a difference. The given is the square of the difference of A and B, and according to this third special product rule, the square of a difference of A and B is equal to the square of the first term. The first term is A minus, the second term is negative, negative twice or 2 times the product of the two terms A and B. The first term is A, the second term is B. And the last term is positive, the square of the second term. The second term is B. These are exactly the terms of the square of a sum of two terms A plus B, except that the middle term of the square of the difference of A and B is negative. For the square of the sum of A and B, the middle term is positive. For the square of the difference of two terms A and B, the middle term is negative. And we can easily verify this third special product rule by applying property of exponent and long multiplication. We verify that the square of A minus B is equal to A squared minus 2AB plus B squared. By definition of exponential notation, the square of A minus B, here the base is A minus B, and the exponent is 2. And A minus B squared means that we multiply the base A minus B by itself 2 times. That is why the square of A minus B is rewritten as A minus B multiplied by A minus B. We multiply A minus B by itself 2 times, or we rewrite A minus B 2 times because the exponent of the base A minus B is 2. And to remove the grouping symbols, we apply the distributive property and the property of exponent. We start by distributing A from the left side, or we multiply each term of the second binomial by the first term A. We have A multiplied by A by property of exponent. We copy the common base A, and we add the exponents of A. Exponent of A here is 1, plus the exponent of A here is 1. Hence, we get 1 plus 1 is 2. Next, we multiply A by negative B. This is positive, multiplied by negative is negative. And A multiplied by B, the product is AB. Now we distribute negative B from the left side, or we multiply each term of the second difference A minus B, or the second binomial A minus B, by negative B. We have negative B multiplied by A. The sign of A here is positive. Negative by positive is negative. And B multiplied by A is BA. But by commutative property of multiplication, the product BA is the same as AB. Hence, we write AB. Negative times positive is negative. B multiplied by A, we write as AB. Finally, we multiply negative B by negative B. Negative by negative is positive. And B by property of exponent, copy the common base B. And we add the exponents of B. Exponent of B here is 1. Plus the exponent of B here is 1. Thus, 1 plus 1, we get 2. After removing the grouping symbols, we combine like terms or similar terms. And the middle terms are the like terms. They have common literal coefficient of AB. And to combine like terms, we add the numerical coefficients of the like terms. The numerical coefficient here is negative 1. Numerical coefficient here is negative 1. The first term is as is, the square of A. First term is A squared. And the second term is negative 2. Negative 2 is from the sum of negative 1 plus negative 1 is negative 2. And the common literal coefficient is AB. The product AB. And the last term is the square of B. We have shown that the square of a difference of A and B is truly equal to the square of the first term minus twice the product of the two terms. The last term is positive, the square of the second term B. We now take an example for applying the third special product rule to get the square of 3x minus 7y. We want the square of 3x minus 7y. The square of 3x minus 7y. Comparing with the third special product rule, our A is 3x. And our second term B is 7y. In this example, the square of 3x minus 7y, we apply the third special product rule because the given is, in the given we have the difference of two terms. And the third special product rule applies only when the given is when you have the difference of two terms in the given. And by the third special product rule, the square of 3x minus 7y using A and B is equal to the square of the first term, A, minus twice the product of the two terms, plus the square of the second term, B. And we substitute the values of A and B. A is 3x. The square of 3x minus 2 multiplied by A is 3x multiplied by B. B is 7y plus the square of the second term B denoted by B. B is 7y. The square of 7y. And we simplify each term by property of exponents. The square of 3x equals the square of 3 times the square of x. The square of 3 is 9. Multiplied by the square of x, x squared. Negative 2 by 3 is negative 6. Negative 6 by positive 7 is negative 42. Negative 42 multiplied by x multiplied by y. And the last term is positive. By property of exponent, the square of 7y equals the square of 7 times multiplied by the square of y. The square of 7 is 49. Multiplied by the square of y, or y squared. And that is the 9x squared minus 42xy plus 49y squared is the square of the difference of 3x and 7y. We take another example for applying the third special product rule. The given is the square of 2u plus v minus 3w. The given is the square of a trinomial, but we only have special product rules for the square of a binomial, where we have addition between the two terms or we have subtraction between the two terms. So what we will do is we will rewrite the given to express the given as a square of a binomial as either the square of a sum or the square of a difference. if you rewrite this as the difference of 2u plus b and 3w, then you will apply first the third special product rule for the square of a difference. And then you will apply the second special product rule for the square of a sum. If you rewrite this as the square of the sum of 2u plus v minus 3w, then you will apply first the second special product rule for the square of a sum, and then you will apply the third special product rule for the square of a difference. I will rewrite this square of trinomial as the square of a sum, or the square of a binomial with addition between the two terms. I will write this as the square of 2u. I will take the last two terms as one quantity, v minus 3w squared. Now we have written the square of this trinomial as the square of binomial, or the square of a sum of 2u and this quantity v minus 3w. And to get the square of this sum, we apply the second special product rule, which says that the square of a sum is equal to the square of the first term, 2u, plus twice or 2 times the product of these two terms, 2u and v minus 3w. And the last term is positive, the square of the second term. The second term is v minus 3w. The square of v minus 3w squared. We simplify each term. The first term is the square of the first term, 2u. 2u is squared. We simplify each term by applying property of exponents. And to the last term, to get the square of the difference, we apply the third special product rule for the difference, for the square of a difference. For the first term, by property of exponent, the square of 2u equals the square of 2 multiplied by the square of u. And the square of 2 is 4. Multiplied by the square of u, u is squared. Multiply 2 by 2, we distribute 2 and 2u to each term of this difference. 2 by 2u is 4u. 4u multiplied by v, the product is 4ub. 4ub. Next, 2 by 2u is positive 4u times negative 3w. Positive 4 times negative 3 is negative 12. Multiply by the literal coefficients u and w. To the square of the difference, we apply the third special product rule, which says that the square of the difference is equal to the square of the first term. The first term is b squared plus b squared plus twice the product. Twice the product of the two terms. The two terms are v and 3w. v and 3w. Since we have the square of the difference, the product is equal, the square of this difference is the square of the first term, v squared. The second term is minus twice or 2 times the product of these two terms, minus 2 times the product of these two terms, B and 3W. And the last term is positive. The square of the second term, 3W squared. We simplify the last two terms. We have 4U squared plus 4UB minus 12UW plus B squared. We have negative 2 by 3 is negative 6. Negative 6VW. And by property of exponent, the square of 3W is equal to the square of 3 times the square of W. The square of 3 is 9. Multiply by the square of W is W squared. And this is the square of the trinomial 2U plus B minus 3W. In the next lesson, we will complete the special product rules. We will take the cube of a sum and the cube of a difference. If you have question about the lesson today, about the first three special product rules, you ask your questions in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalisan. Thank you.